Hello everyone, my name is Hongjiu Wang, and as for ESE 5230's quantum engineering video project, today I'm going to give you a brief introduction of silicon germanium lithographic quantum dots. So first of all, quantum dot is a kind of confinement of electron within nanoscale potential wells. Uh, their energy level is discretized because of the confinement, and this enables quantum properties. The motivation of this architecture is that from scientific need, quantum computing requires high-fidelity, scalable qubits, while the traditional, like superconducting or ion trap technologies, they have integration challenges, and also they are very costly. While the silicon germanium lithographic quantum dots is highly integrable with existing silicon chip nanofabrication technology. As for the applications, silicon germanium quantum dots is used for quantum computing. For example, the scalable quantum processors like Intel's hot qubit architecture, and on the bottom left is one of the Intel's 12 hot qubit architecture chip. It can also be used for quantum communication. For example, it can be integrated with single photon emitter or detector. And one of the example is the uh, superconducting nanowire single photon detector, which is the picture on the bottom right. Lastly, it can also be used for precision sensing, like application in nanoscale magnetic or charge detection, like medical imaging and material defect analysis. Some examples of competing technology. First one is superconducting qubits, which are quantum bits based on superconducting circuits using Joseph junction in superconducting material to manipulate quantum states. And by adjusting the current and voltage in superconducting circuits, quantum states like 0 and 1 states are manipulated for superposition and entanglement. The advantage of the advantage of this setup is that it has fast gate speed, mature control techniques, but it requires extreme cryogenic environment to the millikelvin level, and scalability is also a challenge, and it has shorter coherence times, requires complex error correction techniques. The second kind is ion trap. Ion traps are ions that are trapped by electromagnetic fields as quantum bits, with their internal energy level manipulated by lasers. Laser pulse control the energy level transition of ion to achieve superposition and entanglement of quantum states. So the advantage of this technology is that it has long coherence times and high fidelity. And disadvantage is that the system is very bulky and very hard to operate, and it also faces the scalability problems. The third one is the topological qubits, which are quantum bits based on topological states of matter using quasi particles in topological material to encode and manipulate quantum information. Uh, so theoretically, this one is inherently robust against external noise and local perturbations due to their property. But this one is more like is still being experimented, so we're not going to talk a lot about it. Comparing to competing technology, the silicon germanium quantum dots, the advantages are they have high scalability because it is directly integratable with the semiconductor industry, and it has compared to the superconducting qubits, it have relatively long coherence times and relatively low cryogenic requirement, which is about 1 Kelvin, much larger than the millikelvin level of superconducting qubits. Disadvantages. So compared to the superconducting qubits, it has relatively slower operation speed, and compared to both the superconducting qubits and ion traps, it have relatively low technological maturity, and it also requires some error correction. Here we provide a brief historical overview of quantum dots. So first quantum dots was invented by the Soviet scientists, but it was quite different than the silicon germanium quantum dots, because the first invented quantum dots was more colloidal quantum dots, which are nanocrystals of 2 to 4 or 2 to 5 or 3 to 4 materials synthesized chemically in solutions, while the silicon germanium quantum dots are solid state quantum dots based on semiconductor technology, typically grow on wafers and using technique like molecular beam expertise or chemical vapor deposition. And secondly, the colloidal quantum dots are smaller compared to the silicon germanium quantum dots, and they're often spherical, but their relative size and shapes are harder to control precisely, while the silicon germanium quantum dots can be precisely controlled using lithography. And lastly, for application, colloidal quantum dots are mainly used in optical applications such as display, the quantum LED, and the solar cells, because their relative size make them because their relative size difference make them able to fluorescent with different wavelengths, while the silicon germanium quantum dots are primarily used in quantum computing because they have very precise control. As for the silicon germanium quantum dots, most of the breakthrough happened in the last 20 years. As for 2004, Netherlands scientist Leo Kovenhagen first showed single electron control in semiconductor material, and later in 2012, also in the Netherlands, Gerard J. Blasch first showed silicon germanium heterostructure double quantum dots. And in 2018, because of the advancement in lithography, DM Xerox showed high uniformity germanium dots array via advanced lithography. Here I want to talk briefly about the principle of technology. The first part, why we choose lithography silicon germanium. So first of all, we have talked about the quantum confinement effect. So when electron's motion is confined within a nanoscale quantum dots, its energy level becomes discrete, similar to like electron level in an atom. And so why we choose silicon germanium as the base material? The band engineering flexibility allows us to change the silicon germanium band offset in the heterostructure, which is very useful if we want to change the quantum dot potential well. And lastly, because this material have long coherence time, so silicon, especially when isotropically purified silicon, have low nuclear spin noise, enable long qubit coherence times, usually in the level of millisecond range. And as for lithography, one of the most important tools is photolithography machine, which we see here is an extreme ultraviolet photolithography machine. Combined with photomask, we can achieve the pattern we want. When the photomask is placed on the photolithography machine, the light passes through the photomask, shine on the wafer, and the photoresist on the wafer, depending on its positive or negative photoresist, it either becomes hard or soft, easy to if it's hard, the remaining part is removed, and if it becomes soft, the part that is shine is removed, and then later it forms the it forms the three-dimensional pattern we see here. The entire top surface is then under either wet etching or dry etching, or maybe we should call it chemical reaction. The part that photoresist remain will protect the substrate, finally making the desired three-dimensional pattern we want. So here's the cross-section view of the fabrication process. On the bare wafer, we deposit a layer of metal or aluminum on it, and then spin coat photoresist. After that, we expose and develop the photoresist, so we can see those trenches. The aluminum under the trenches are not protected, so they will be etched away by a chemical reaction, and then we also remove the photoresist. And then basically it's just the same kind of process flow again, and then we can get the final structure we see on the reference paper. Lastly, I want to talk about the control technique. So after we get the final device, which is the picture on the upper right, it can trap up to 2 electrons in the silicon layer by the left and right electrode. They can be changed to different voltages, and then the different magnetic field is applied on the left and right to achieve different Zeeman split. And then the microwave is used for spin control, and the electrode amp, the voltage on it can be changed to control the tunneling barrier from the left to the right. And the control process is somehow similar to the Coupin's 2006 article we have read on Perusal. As for the state-of-art feature, we have single qubit coherence, horizontal decoherence time larger than 28 millisecond, and dephasing time larger than the 180 microsecond. And secondly, the 2-qubit CNOT gate fidelity. We have 99.5% for single qubit and 78 for Bell state, which is the one from 2020 reference article. Another paper published in the Nature showed high density two-dimensional crossbar consists of a total of 16 arrays, 16 quantum dot array. And lastly, we have quantum circuit control based on CMOS, which is from 2021. This one is really important because for the Euro method for quantum for qubit control is a single qubit is wired through a single wire, because the normal CMOS chip is not working under cryogenic conditions. This one have solved the so it would be really hard if we have, like, say, millions of quantum dots, which requires millions of wires. This one have integrated the quantum dots onto the CMOS control, which have greatly reduced the problem. We still have some challenges of this technology. For example, in case of lithography, we have minor deviation in fabrication. This can lead to performance variation between dots, and also decoherence, which is affected by charge noise and nuclear spin noise, especially in the non-purified silicon material, and also thirdly, scalability. So crosstalk between dots and signal routine become complex, limiting the system scalability. And lastly, the defect at the heterojunctions interface can affect the performance and stability of quantum dots. But overall, all this should be able to be addressed by improvement of fabrication process. And lastly, as for the outlook of this technology, we should see the operation temperature improvement, which is from millikelvin to around 1 Kelvin, even to 3 Kelvin. And scalable control of more than 50 quantum dots array, which is from the IBM's roadmap. And for even longer, for even greater vision, we might be able to see, like, all silicon quantum processors, which is like millions of quantum qubit scale. Thank you for listening. And here are the references I have used.